We're pleased to have Antti Kupiainen, who's going to tell us about diffusion of energy in coupled map lattices.
Okay, thank you for the invitation to talk here. So what I want to talk is some joint work with Jean Bricmont on diffusion. So it's not exactly on localization, it's actually the opposite of localization, namely diffusion, but maybe it's a little bit connected to what's in this. However, the setup will be classical dynamics, and again the setup will be classical dynamics, a bit of the type of the quantum dynamics what you are interested in, namely Hamiltonian dynamics. So when you think about Hamiltonian dynamics, does it work? No, doesn't seem to work. No.
You have a stick here. Maybe better.
Well, but it just worked for a second ago, so there must be something. Anyway.
If you want to use this very imposing stick.
That's better, yeah. Okay. So if you think about Hamiltonian dynamics and you want to ask about statistics of the motion, so what sort of distributions describe the statistics? Of course, if you have a closed system, just the Hamiltonian dynamics, then it's the Liouville measure, or maybe restricted to constant energy. When you have an open system and you are equilibrium, then it's the Gibbs measure. And if you are not in equilibrium, then you basically don't have a notion. You have a notion, but you don't have such a formula. So what do I mean by open system? So by open system, I mean that you imagine this Hamiltonian system interacting with some sort of exterior and environment. One way to model is by noise. Once you add a little bit of noise, you have a Markov process, and you can look for a stationary state. And the terminology is then that you are looking for a non-equilibrium stationary state. And if this noise, in some sense, is uniform, come back to it in a moment, then you are in an equilibrium situation where actually the state is just Gibbs state. You can ask the same question, rather not coupling it to noise at all, but just asking about return to equilibrium. Namely, take a closed system and take an initial distribution which is close to the Gibbs measure in some sense, and let it evolve with Hamiltonian flow, and then you would like to show that it has irreversibility in the sense that as time goes to infinity, you flow back to the Gibbs state. Okay, this sort of statement literally can be true only in infinite dimensional systems in infinite volume. But those are two ways to look at this, the question of non-equilibrium, either perturbing equilibrium or driving it by external influences. Yes. So what I want to talk about are just these cases where I have a large system. So what I mean by that, I want it to be extended in the sense that it has some spatial structure. It's in a volume, and so if it's a dynamical system, then the attractor should sort of scale with the volume. The number of relevant degrees of freedom should go like that. Examples are PDEs, where you just take bounded data, so take PDEs in the whole space and bounded data. Take n-particle Hamiltonian systems and take the number of degrees of freedom to infinity. So these are PDEs, these are coupled ODEs, if you wish. And then the utmost discrete cases, you take just discrete space and time PDEs, which are called coupled map lattices. So you discretize both space and time, and then you do some dynamics there. Now, once you have this thing that you are looking at, this extended dynamics, you can get something which you don't see in finite dimensional systems, both in the Hamiltonian context and also in dissipative context. You can see patterns, spatial patterns, and you can see diffusion and transport, and that's the issue of this talk. So think about having an extended system. So here's the box, and there's some Hamiltonian dynamics inside. Put some noise on the boundary of the system, so there's some external influence, forces coming, random forces, for instance, coming from the outside. When the amplitude, in some sense, of these forces are the same, then we have the equilibrium system. So we are putting energy from the boundary sort of uniformly, and when they are not the same, then you can have flux of energy through the system, and you have a non-equilibrium situation. Again, the same question posed in infinite volume and no noise would be just, as I said, to take Gibbs state, something which agrees with the Gibbs state at spatial infinity, and then take such a state and evolve it under Hamiltonian dynamics and show that there is a diffusive approach to equilibrium state. Okay, so these are the sort of questions I'd like to consider. Now, these kind of issues have been discussed a lot during ages, and also quite recently a lot. Mostly in terms of something what I would call coupled flows or coupled maps. So, coupled flow would be just you take the discrete wave equation. So you're on the lattice, and that's the nearest neighbor Laplacian operator. And look at this is a Hamiltonian system, and look at that system. So concretely, it's just a bunch of coupled oscillators. If I have here, like I have U cubed here, they are anharmonic oscillators coupled to each other. At each lattice side, I have an anharmonic oscillator, and then I couple them together. Such a system, actually, well, certainly there's lots of numerics on it, but also you can formally sort of take a scaling limit if you take this anharmonicity very weak. So I'm talking about weakly nonlinear systems. If I take this to 0 and at the same time scale space and time in an appropriate manner, there is a limit where, at least formally, the evolution of the state. We started with some state probability distribution in the beginning, and the evolution is controlled by a Boltzmann equation. Now, once you have that Boltzmann equation, it's just a partial differential equation which you can study, and in that case, you can study the questions which I will be studying later, namely diffusion and Fourier law. But the problem here is that it's very hard to get mathematical control of that, to prove a kinetic limit or to go beyond it. Okay, the situation, the lambda here is like if you take a random Schrödinger operator and you take the coupling, the amplitude of the potential small, then in certain cases you can, in those situations, prove again what I would like to prove is diffusion, and what you succeed typically proving is that you have diffusion up to certain time scales. And if you take a scaling limit where take the coupling to 0, you then get Boltzmann equation and things like that. So this is the analogous situation in classical dynamics what has been studied.
So you need the lambda. You need nonlinearity just to prove
without the nonlinearity, the system is completely integrable, and actually. From the point of view of heat conduction, it's a superconductor, so it's not what you want. Now there's a completely opposite limit. So instead of coupling sort of strongly weakly anharmonic systems, couple weakly strongly anharmonic systems. That's the other end of the spectrum. So that's what I want to talk about, actually, namely. The sort of systems is that you take coupled together very nice hyperbolic Hamiltonian systems like billiards or Anderson systems, or discrete version of such a thing, which is discrete time version of such a thing, so coupled maps. So let me give you a picture of so this picture goes back to some work by the first 4 people here. When was it? Long time ago. 92. Okay. So they were considering playing billiard on the table. The white part is the table, and here are the obstacles. So you put at each table a ball, and when the obstacles and the parameter is this distance here, so you can sort of change that. So of course, when this distance is 0, each ball just plays is on its own table, and they don't know about each other. But when you increase it enough, then they have a chance every now and then to collide with each other. But if it's not too big, they don't leave their tables. So this would be a system where you expect to get transport of energy through the system, but not transport of particle, but no particle transport, but transport of energy. And there is a control. There's a parameter. So this is my weak coupling. When this is small enough, this is uncoupled. So this doesn't know about its exterior, no, does that. And once I turn it on weakly, I will have mostly chaotic motion here, and every now and then I collide with my neighbors. Okay, so that these 4 people here prove that in a finite box, was it only one dimensional, or it was any dimensional? Finite box, you are a K-system, right? So it's pretty mixing. But of course, we'd like to get a little bit more, namely to understand transport really, and to show that energy is diffusing in such a system. Okay. What's the if I abstract this model, what would it be? There is a total energy which is sum of local energies. So x is the lattice site which is parameterizing the table. So each ball has its own energy, and my total energy is sum of the local energies. When there's no coupling, I call coupling this parameter which allows these guys to interact with each other. When there's no coupling, then each local energy is conserved. Okay. When you turn on the coupling, then typically, and in this case, only the total energy is conserved. Of course, it's a Hamiltonian system, so this thing is still conserved in time. But the local guys satisfy an equation like this. So the time derivative of the local energy is a divergence of a flux of energy at that site. Okay, so now the issue here would be now to prove that this local energy is diffuse, and actually this flux here, which is some function of the positions and momenta of the system, this flux here in the long time is tied to these energies by something which is called Fourier law. So let me make that statement a little bit more precise. For instance, let me pose it in the return to equilibrium problem. So take an infinite array of these guys. Take an initial state, say Gibbs state, for instance. Take and move it under time. One way to pose the problem is to ask about hydrodynamic limit, namely take E means expectation. So take expectation in the initial state of these energies to be some slowly varying function. So I take a state where they vary slowly in space, so parameter epsilon, and then take the diffusive limit, namely compute the energy at some x over epsilon, scale the time by epsilon squared, take the average on the dynamics at that time, and take epsilon to 0. Okay, so then you get something which depends on time, the rescaled time and space. In the same way, take this current here and measure it also in such time scales and length scales. And we would like to show that these things are well defined and actually are related to each other. Namely, this current in that limit will be will be proportional to the gradient of the local temperature, and then if that were the case, then this conservation law becomes a parabolic equation. Namely, tau dot is given in terms. You have some conductivity matrix in between and derivatives of tau. So that would be one way to pose the problem. Actually, in this very chaotic system which I have, this statement certainly should hold almost surely in the initial measure. So that's one way to pose. Another way would be to take this non-equilibrium stationary state. Maybe I don't repeat that story too much here, but it's sort of obvious. You scale everything. You're taking infinite volume, but you scale it back to unit volume, so unit scale. So you have the system on a finer and finer lattice, and you you do the obvious scalings and ask for the non-equilibrium stationary state. Again, compute the current, which now doesn't depend on time because it's stationary, and the average energy. And in the limit, as your scaling parameter goes to 0, you would like to show that you have an elliptic version of the previous parabolic equation. So you would have temperature distribution, which is given as a solution of this elliptic problem with the given boundary conditions, what I put in the beginning. So these are two ways to state the question what I'm dealing with. Okay, so let me now go to what I want to do is I want to cook up discrete time dynamics, which would be a model for what we were just saying. Okay, so for that I need the concept of coupled map lattice. There's nothing really here. These are just discrete time PDEs, so this in the following sense. So your dynamical variables, you take a lattice and put at each lattice side some variable living in some space, m, say, think about spins or something, so there could be r or some manifold in general. And so those are the variables, and take a dynamics which mapping these guys to each other, which is local in the sense that once you compute the new spins, then the thing at position x depends mostly on nearby guys. So you could even take it that just depends on nearest neighbors. But anyway, it depends weakly on far away guys. The extreme case is an uncoupled dynamics, namely one where you just take each of them performs its own dynamics with the same map, and they don't know about each other. This is obviously analogous to my billiards when I have the coupling to 0, and once I turn on the coupling, I get something which mixes the things together. So what I would like to have here is something, if I want to mimic what this Hamiltonian system, I should have my degrees of freedom should consist of these conserved guys. Let me call them energies, like E, and then the other degrees of freedom. In the Hamiltonian system, I have the energies conserved, and if I go to then there is the continuous time direction, but apart from that, it's a hyperbolic system. All the Lyapunov exponents are non-zero in the billiard case. So let me take sort of call theta all the other degrees of freedom, and let my model be uncoupled model be the very simple one. Nothing, the energies, nothing happened to them, and the other degrees of freedom just perform a chaotic motion. For instance, you could take theta just an angle on the circle, and the motion being theta going to 2 theta. Or you could, if you want to be closer to Hamiltonian situation, you would take a torus map as your chaotic degree of freedom. Okay. So this is, of course, a completely trivial dynamical system. Each of the energies are conserved. Nothing happens to that, and the rest are just performing chaotic motion by doubling of the angle. Now, once I do the coupling, I typically remove this degeneracy of each, like in the case of the billiards, and I want to look for a coupling so that the total energy stays fixed. So let's write it like that. Without those terms, I have just the previous thing, nothing. This is the new guys after one time step. And this is the uncoupled dynamics, and then I add something. I add something which is, as I said, local. So it depends, this function depends only on e's and thetas close by. But I want, in order to have the total energy conserved, I want this to be 0 for all theta and e. So one way to do that is like I have in the Hamiltonian system. H dot was divergence of a current. So one way to do it in this couple map is to just take such a thing. So I take my coupling such that it's a divergence of a local function. If that's the case, then I have trivially the total energy conserved. So this is the class of dynamical systems which I take to mimic what the Hamiltonian dynamics is doing, and I would like to understand in general in such a class of dynamical systems how to get diffusion and transport. Okay, so the statement would be which you would like to prove is the following. To repeat what I said before, so take an initial condition for the energies such that at infinity they become constant. Something, let's call it temperature at infinity. So this is the analog of the Gibbs state being constant at infinity. And show that for almost every initial condition of these chaotic variables, your energy is approach to the limit at t in a diffusive manner. Sort of analogous way to pose the same thing is to take an initial condition which is slowly varying, as I said. Put a parameter epsilon there, and rescale space and time. Take epsilon to 0 and show that the energy is rescaled in such a manner satisfy the nonlinear diffusion equation. Again, this deterministic equation, this equation independently of what your initial condition is. Okay, that's a sort of two ways to pose analogous ways. One is sort of corresponds to taking localized initial data and just asking what happens, how it diffuses away. The other thing is to take very spread out initial data, rescale everything, and to show that you get this. A slightly different aspect. So let me first look at the fast, what I would call the fast variables. There's nothing. Let me take first the case that this fast dynamics. These guys don't depend on the energies. And things are pretty clear. Here is the chaotic dynamics, and if I take this as a small perturbation, it doesn't change very much. It couples the things to each other, but the dynamics of these variables is space-time mixing. That means that if I pick a typical initial condition, then the resulting trajectory is a random process, which is weakly correlated in space and time. So if I transport Lebesgue measure of these guys in time that translates into trajectories which are weakly correlated in space and time. So these thetas act like noise with weak correlation in space-time noise. So they provide a random environment for the motion of these energies. Here is my dynamics of the slow variables. Let me write it like that. So E at time t plus 1 minus E at time t is divergence of this current. So what we have is that these thetas are weakly correlated in space and time. So these are, I view them as random variables now. So if I want to prove that these energies diffuse, almost surely in the initial condition, it's the same thing as to prove quenched diffusion for this guy. So I have randomness, and I want to prove a quenched diffusion. Namely, I pick my randomness, I fix it for once and for all, and with probability 1, then I have diffusion in the runtime.
But don't your thetas undergo some dynamics too, or not?
Thetas go, yeah, of course.
So they're not independent guys at all.
Well, but they are weak. I mean, if I take theta going to 2 theta, then I get basically coin flips.
But aren't the thetas at different places coupled, or are they not coupled?
Yeah, sure.
They are.
Yeah, but the statistics of the thetas has statistics of the thetas is weakly correlated in space and time. So the correlation function decays both in x and time.
But can you quantify what you mean by weakly? I think that's the point here.
Yeah, well, I mean, what I mean by that is that if I look an observable at the of the theta at x and t, let's take another observable at theta at origin, and then this thing, and I take the average over the initial conditions. So let me denote it by brackets. Then this converges either as I take the spatial separation to infinity or the temporal separation to infinity exponentially fast, just the average of the two guys.
But you have that's just a known fact from these couple.
Sure. Yes. Yes. I mean, once I have no coupling, then
I understand.
Yes, and once I put a little coupling, then you do the usual song and dance through symbolic dynamics. You get the Hamiltonian, which has exponential interactions which die exponentially.
You go through symbolic dynamics.
Sure. Yeah. So both that you can do in the hyperbolic case or in the expanding case, like I'm thinking about here, or in the symplectic case, like when you have the Tarot automorphism. And this is true for hyperbolic. If you have a uniformly hyperbolic system, this is the standard result.
So even if you couple,
once you couple, you have to be a little bit careful with smoothness. So you have to take. If you take these maps analytic, then it's sort of straightforward. If they are slightly less, then you have to work more. But this is a standard thing. Okay, so let's think about this thing where I have sort of I have a discrete version of a random drift, right? So J depends on my dynamical variables. I mean, this is, and then there is this randomness there, which is short correlated in space and time. Now, the first, we want to prove quenched diffusion for it, but the first thing is to look at annealed case, right? So take an average over the thetas. If I take the average over the thetas, so I take the invariant measure of the theta, I take the average, then what I will get in general if I have a system like that, where if I assume that my model is set up in a translation invariant manner, so that the dynamics at translated points has the same form as the dynamics at the original points, then what happens is that this thing gives rise to something like the follows. So the annealed model should look, that of course now needs assumptions on what the J is. But let's say that it's pretty obvious that it should have two derivatives like that. So it should be of the diffusion type, the equation. What I will do later is that I will of course take models which have such an annealed dynamics, and then I try to perturb randomly about that.
What do you mean by stationary state of theta?
Well, I mean,
Is it the whole or?
well, I mean, theta, take the, I have this theta dynamical system, so it has a stationary measure.
Individual?
No, the
theta.
full, the whole.
The full.
Thing. It has a stationary measure. So take my initial conditions distributed.
Why does it have stationary measure?
Because it's a hyperbolic system. It's an expanding coupled map lattice, so it has a Sinner-Royal-Boyer measure. And that is given explicitly in terms of a Hamiltonian of the spin system. So there's a stationary measure. I take my initial conditions. It's actually absolutely continuous with respect to Lebesgue measure, this invariant measure. So if I take my initial condition distributed according to the stationary measure,
So what's the Lebesgue measure?
the infinite
The
product.
infinite?
Yes,
The infinite product of Lebesgue.
yes.
Right. Those.
Well, we are infinite product of circles, so that's
Right. So the initial measure is absolutely continuous with respect to.
right. I mean, that's very simple. If you take no coupling, right, then it's just a product of
So
Lebesgue
just
measure.
a local perturbation.
Then it's just a product of Lebesgue measure. Okay, and once you have something, you get the density which couples a little bit the thetas to each other. Okay. So I get something like that. So here I have the random drift, and the annealed case would in general be a nonlinear discrete diffusion equation. Now, if I write the full thing now, the full thing here, in terms of the average and the rest, if I call the thing minus its average the fluctuating part, then my slow dynamics would be something like this. So I have an elliptic part, and I have a random drift. So this is what I start with. I will take a class of couple maps which give rise to such an equation, and I try to control this equation. So if I have just this elliptic part and it's nice enough, then I have like a nonlinear parabolic equation, and that's what I want to get. And then I have the random drift, and I want to show that this random drift, once I look at this long time limit, the only effect of the random drift is to renormalize the conductivity here. So a long introduction to get into studying parabolic equations with the random drift.
Nonlinear.
Nonlinear. But at least if you think about this Hamiltonian system, something like that should come out of it. Of course, everything is in the details, so in that case, this is probably pretty bad from the point of view of what, yes?
Just a question of understanding. I mean, this weak coupling limit that you're considering there, that would exclude that you describe any form of sort of low temperature phase. Metaphorically translated.
Yeah, well, I mean, I'm certainly not envisioning of having any phase transitions in this system, if that's what you are asking.
Would you be in a high temperature phase?
Well, I mean, from the point of view of sort of mathematical physics, I would be in high temperature in terms of expansions and decoupling and things like that.
Shear dynamics, of course.
Yep. Okay, let me show you how this thing is done when you replace this nonlinear problem by a linear. And what then we do, we make a perturbation of that analysis. That's all what we do. So what would be the linear? If the thing is linear in E, then then linear means that it's just a matrix, right? Which depends on these random variables theta. For the energies to conserve means that these guys sum to 1. And if I also assume that they are non-negative, which is not necessarily true in the case of my Hamiltonian system, and that actually turns out not to be important. What turns out to be important is this conservation of probability. But if they are also non-negative, then I can interpret this as transition probabilities of a random walk. So I have nothing, my model is nothing but a random walk with transition probabilities which depend on time through this theta. And space.
And space.
And space.
And
my energies are just the probabilities of finding a walker at time t at point x when they start at origin, say at okay. So it's nothing but a random walk in random environment because remember thetas were random. I told that they are exponentially mixing. So that means that these matrices here, which depend on space and time, have correlations which decay exponentially, weakly, both in spatial and temporal direction. So I have a random walk in a random environment which is weakly correlated in space and time.
But you also have the fact, I mean, if I understood correctly, your P's also depend on the E's. No?
Yes, my true, but I'm
Oh,
now
you're
trying to be
idealizing.
pedagogic and take the linear model first, okay? Because the way we've set up renormalization group for the nonlinear problem will be modeled out of this, and it's easier to explain this. So let me try to explain this. I don't know if I succeed, but that's the purpose now. So here the problem is then to prove quench central limit theorem for such walks, namely you pick up randomly these guys, and then you want to say that with probability 1 you have diffusion. So how do you do it? Well, if you consider a random walk in space-time dependent with the space-time dependent transition probabilities, then and now you're walking. Let me call the walk omega. So these are points on the lattice. So you walk from omega 0 to omega t in time t. Then the probability for such a walk is then, of course, just the product of these individual jumping probabilities.
Antti, your random environment is independent on the random walk.
Independent of the random walk, yeah. I'm not sure what you mean by that. But statistically, yes.
Is it the consequence of linearity?
That's a good question, because once you get nonlinear, things get more dependent.
That's a consequence of linearity.
Well, you should. I mean, the general case I will be doing, I think you should think about this as, what would be a good example? Okay, if you have a stochastic differential equation, then you can have Brownian motion, which is what I have here, and more generally you will have just drift, which depends on the variables, drift and diffusion constant, which depend on the variables, right. And non-linearly. So nevertheless, you still have the increments are sort of independent, but they depend on, of course, what the variable happens to be at that time. Then the increment is independent. Okay, so what do you want to do with such a thing? So you have that. If you're interested in diffusion, then you compute the mean square. Let me call it E, the expectation in the walks. So you sum over walks. Look at the walk at time t, square it, take the sum over all walks, and divide by t. And if this guy stabilizes as t goes to infinity, you have diffusion. Okay. One way to do this is to go to the scaling limit. Namely, instead of going to long times, bring everything back to unit times. So bring everything back to unit interval by scaling your walk appropriately. And then you want to show that after now you take this parameter t to infinity, what you get is just ordinary Brownian motion. This is familiar to from random walks. So that's just saying that the scaling, you would like to prove that your scaling limit, well, first of all, exists, and almost surely in the ensemble of the p's, of the transition probabilities, almost surely is just Brownian motion with a diffusion constant, with some non-zero diffusion constant. So how do you do this? Let me, I said that everything is done by renormalization group, so I will explain it here, where it's extremely simple to set up. It's a different question than to analyze it. But let me show you how it's set up. There's really nothing particular to implement the scaling. So if you want to walk from x to y during time interval t prime, so then you just, that's a product of these random matrices, t minus t prime of them. Take this product, and then you compute the matrix element of that. That's your transition probability. And I'm interested in this product as the number of entries goes to infinity, and I want to scale that. So let me scale it. Let me define a renormalization group transformation, where I'm putting here as this transition probabilities of the random walks are functions of this random matrix P, because usually you have random walk just with fixed transition matrix. And then you don't note that, but I mean, here I want to say that they are functions of my original random array of transition probabilities. So I compute, what I do is the following. My renormalization group is nothing but I take this product. So if I go from in time t, let me denote it like that. So I have, at each time I originally have a transition probability matrix. Now I go from time t, L squared time t, to L squared t plus L squared. So this is time interval of length L squared starting from that time. And I rescale space by L and also the value of that. So that way I get a new matrix indexed by the lattice living at time t. Given this random matrix P, this is a new random matrix. It has a new distribution. It's describing walks on a final lattice. And I have a very simple relation between the two things, because I really didn't do anything. Namely, if I look at walks in the old P in time between t and t prime, they are given by walks in the new renormalized B, the shorter times and shorter scales. That's nothing more than that, because I turn the scalings here, they translate here. So this is the renormalization group flow in a space of random matrices. I take this random transition probability, solve the problem up to scale L, compress it back to unit scale, and that's...
So far, all these are just identities, right? I mean, are definitions.
Just definitions. So the scaling, the question of scaling limit then translates into understanding what happens to these random variables as L goes to infinity. So I translate the problem of scaling limit into flow in the space of probability distributions of random matrices. Okay, so for instance, if I compute the diffusion constant at time t, so this guy, it's the same thing as solving a unit time problem with the renormalized traits. These are identities, okay? Everything, of course, now is there that if you are able to control this thing, then solving unit time is not a big deal. It's just the matrix itself. Same thing for the scaling. Same thing for scaling limit, but let me not, for more general observables, but let me not dwell on that. So now if it happens that you are able to show that this thing converges to something non-random, as L goes to infinity, then your diffusion constant will be just given by whatever is the unit time diffusion constant of that non-random matrix. Same thing for the scaling limit. So your limit is a Brownian motion with this transition probability. So what we want to prove is that these guys become non-random as L goes to infinity, as the scaling parameter goes to infinity, and they converge to P star independently of what realization of the randomness you take. So far I'm just long on a list of tautologies, just reformulating the problem of, so everything is now in understanding how these P's behave. And the way to do it is, of course, not to try to do it immediately at L going to infinity, but you do it step by step. Because my transformation was basically just all kinds of scalings. It satisfies the semigroup property, which means that I can, instead of doing it as little L goes to infinity, I can take little as L as something, some fixed number to power n and do iterations. So let me call R just the step where I have some fixed scaling, do it n times, call it Pn, and then you want to understand what happens to Pn as n goes to infinity. Now, the way you do it is that at each step, suppose you have computed Pn, then you separate it into two pieces. You separate it into its average and a fluctuation. So you do that, then you compute the new P, which is a product of these old P's, L squared of them. And you get a new average, which dresses up a little bit the older average, and then new random part. And what you want to show is that these averages, these guys stabilize, go to a fixed point, and the random parts almost surely disappear. If you do that, then you have everything about the scaling limit. Okay, if you are interested, there's a recent preprint where we do this for this class of models, proof along these lines. What happens is that this randomness is irrelevant in all dimensions. So unlike for random walks in random environments, which are temporally not time dependent, there are critical dimensions, here there are none. And that's sort of not difficult to understand because the environment sort of constantly refreshes itself, so you can't get trapped in these walks. So that's what happens. But the idea here was so transform the diffusive long time problem to iteration of fixed time problem composed with scaling. So we do exactly the same thing for the maps. So here's a nonlinear problem now. I suppress most of the time the x here, but instead of, there we had a linear map here in the random walks. Now we have a random function, it depends on time, and e at t plus 1 is this random function applied to new t, and the random functions are almost independent when when you look at them at different times. Okay? What you are interested in is long time limit of these energies when you do the diffusive scaling. So let me write it like that, L to ND, L to 2N. This is just what we were writing before. And if you look at such guys, then since these are just the rescalings of the old ones, they certainly will satisfy some sort of they at further times are given in terms of what they were at previous times, because you have this iteration. So let me call it renormalized dynamics. So these rescaled guys satisfy a renormalized dynamics with some definition of Fn. And this renormalized dynamics I will satisfy an iteration. Okay, so I have dynamics, I do scaling, the dynamical law changes to a new law, and what I want to prove is that these laws converge under my iteration. So let me, there's the old...
Why R is independent of N?
Why R is independent of...
Why is it a step?
It's slightly...
Or T?
T. No, it's R itself is here. The rule of R is here. So if you look at it, these F's depend on T. Okay.
This is
but R
is an exact formula.
This is an exact formula. So you take, if you want to compute the renormalized guy at time T, renormalized time T, you take the original thing at time L squared T, compose up to L squared T plus 1. Okay. So just take this big composition of the maps. All right. So then you get a new F. Of course, it depends on the randomness during this time interval. Okay. Then you do the L to D, which comes from there. There's a little scaling in the energies if you look at things carefully, and little scaling in X. This is exactly the same formula which in the linear case is just the product of L squared random matrices, but now it's a composition of L squared random functions. Okay, there's nothing, the idea is goes word by word. To do long time asymptotics, you want to understand these guys as n goes to infinity. Namely, you want to understand the unit time of the rescale things. Okay. Again, if you translate these tautologies, then these unit time guys, when you change the scale, are gotten from previous guys with a finite number of compositions of the previous laws. So you have a flow in the space of laws and flow in the space of renormalized energies. And what you want to prove is that the law becomes non-random and linear as n goes to infinity. And then as a consequence, the energies themselves go to the Gaussian fixed points. So you want to prove that noise is irrelevant and nonlinearity is irrelevant. Okay, that's the sort of renormalization group formulation of this problem. Okay, so let me tell you what we are. WIP means work in progress. So this is what we think we can now do, which is basically just proving stability of diffusion under small nonlinearity and small randomness. So that's the following. You take just fixed linear random walk, and you add a nonlinear random drift. Nonlinear in the drift, where the drift is really dynamic also, so like I stated a moment ago. So I have the drift, which has the theta variables, the fast variables have their dynamics. They feed into here and take both this guy and that guy small. So take them what I need actually is that they are analytic functions of the variables, local functions. They decay exponentially, the dependence on faraway guys, and small in appropriate norm. This corresponds in PD language that you would be solving, well, let's call it ET, time derivative is Laplacian E, that's the T, and then you add the divergence of some B, which is a function of E and the randomness. Okay, where this is a random vector field with random vector fields once I view the data as random variables. Now, so that's what we can do. So this is a nonlinear perturbation of the random walking random environment, what I just described to you. I think it shouldn't be so. It shouldn't be that hard to replace this reference dynamics here by a uniformly elliptic nonlinear diffusion equation. So replace this part by something like that. Okay, where A is uniformly bounded from above and below. And even the smallness of the noise might be, in some cases, doable because there is a Markovian structure in this system. So, because it comes really from the dynamics. There was recently, for the case of random walks in random environments, in certain such models, one can actually prove non-perturbative results. There was a work by Dolgobiat and Liverani, who were able to do random walks in such environments, not only small perturbations of ordinary random walks. Now, if you go back to the Hamiltonian systems, you could ask what kind of coupled map should model these coupled billiards in the end of the day. Now, it's clear that you will encounter a couple of problems. If you look at these billiards, then you can have rare configurations of the energy. Let's put the billiards in a line, for instance. Then I could have the situation that energy gets depleted from one of these balls. So let's say that I get the situation where it doesn't move or moves extremely slowly. Then, of course, there will be a long time before energy passes through that thing. So I can certainly get rare configurations where I have sort of trapping in the sense that my flux of energy sort of stops and has to wait for a long time. So such things can happen. So that would correspond to sort of partly correspond to the noise getting more correlated in time. We know that these systems, when the noise is really completely correlated in time, these systems can have traps and can be non-diffusive. So that's one potential danger. So even if the anneal system in such this Hamiltonian case probably is okay, the drift is not clear that it's easy to sort of accommodate it to the anneal. Well, some of these issues can be studied with the randomization group. If I instead of take exponentially correlated in time random walks, I can take them more slowly correlated, and I can do the study whether things still are irrelevant under scalings. So that's the prospect on the Hamiltonian systems. So to conclude, what I want to say is that in the framework of these coupled map lattices, and presumably in the framework also of continuum models, you can study and get such conserved systems using the renormalization group. Another class of problems which this kind of renormalization group might have some uses is when you look at particle systems or interacting random walks and things like that, and you want to study their long distance behavior, the hydrodynamic limits of such systems. So this is something what we are trying to think about along these lines. Of course, the real Hamiltonian systems are a challenge, and it's not clear that the billiard is the best thing. Really, the billiards have their own problems, and maybe something softer than billiard might be more feasible. Okay, so that's what I want to say. Thanks
Very much. So we got some more questions or comments?
When we think about the approach to equilibrium, the reversible approach, we like to think that following Boltzmann, there is some entropy, and that it might be useful to look at it.
Mm-hmm.
For you, that doesn't seem to be the case. Entropy doesn't appear in the discussion, although it's there, but apparently it's not useful.
Yeah.
I guess you're just trying to get convergence to a hydrodynamic equation, and then once that's taken care of, everything else follows, and you don't need to think about the entropy.
Yeah, that's especially in these strongly chaotic systems. I don't really see what the entropy would really. I mean, you can study it separately, but how it would help my study, that's not clear at all. I think the main thing is to get this diffusive. The idea is that there at least in these cases where there's separation of degrees of freedom, the uncoupled system has this infinitely many conserved energies. So you have these Lyapunov exponents which are zero, and once you start coupling, they sort of little open up. So they split away from zero, and in the limit when the system becomes very big, you should get some sort of spectrum of Lyapunov exponent which is responsible for the diffusion. But once you look at it from this point of view, you see that this should really come from something like what I was trying to argue in the beginning, that once you look at the annealed system, there is not much else what could come. That you always get these two derivatives, which is the diffusion. Then you have hard time working proving that the fluctuations are not screwing up this thing. But I think that's sort of.
But you would have some kind of H theorem here or not? But it doesn't work, or?
Well, you have H theorem in the limit. If you look at the Boltzmann equation, I mean, if I can derive in certain limits a Boltzmann equation, which again has an H theorem. But again, it's not clear to me what good it is for me in terms of when I try to get hold of this diffusion in Boltzmann equation. I don't really need either.
Once you put the
Boltzmann
you want to
equation.
get to the Boltzmann equation.
Let's take the much simpler problem. Just take a Boltzmann equation. How do you get diffusion there? H theorem might be useful when you are really very far from equilibrium, and then it tells you that you are getting closer. But once you want to see that the diffusion comes, you have to identify the fast variables and the slow variables. It's exactly the same thing in Boltzmann equation. And the slow variables, the fast variables just get slaved to whatever the slow variables are doing, and then the slow variables diffuse. That's how you deal with Boltzmann equation. And I'm trying to do the same thing for the full system, which is very clear how to do it in the Boltzmann equation. So I want to do this separation to fast and slow, say that the fast is slave to the slow and the slow diffuses.
I have one more. So you did this by scaling, and my question is, if I think about this not only your stochastic PDE or ODE, which you're studying, yes, PDE. So, can you study it beyond the usual time scales, or how far can you go? In other words, can I study this for? Can you?
Well, this is for all time.
It is all time. So you're not
Well, the result for this discrete PDE is for all time scales.
all time scales.
It's really telling exactly what I said, namely the solutions behave like the solutions of this, slightly renormalized. It's not like these kinetic limits where you take.
That's what I'm asking. Yeah. So you don't.
I don't have even that at my disposal because my problem doesn't have such a weak nonlinearity parameter, which is there.
Okay. Well, if there are no other questions, let's thank